In this video, we'll show you how voltage, current, and resistance tests can be used to diagnose charging system problems on Polaris snowmobiles, watercraft, and ATVs. We'll see some tips and reminders on battery testing and maintenance, and how a few simple tests can verify charging system operation. But first, let's review some of the basics of electrical theory. Simply stated, electricity is the flow of free electrons in a circuit. Electrons are the basic building blocks of electricity, which needs three things in order to be useful to us. First, we need something to supply or push electrons. Next, we need a path or complete circuit starting from and ending at the source. And finally, we need something to use the electrical power, say a hand warmer or a headlight. This is often referred to as the load. Let's look at this water analogy to help us understand and remember the relationship between voltage, current, and resistance. Electricity flowing through a wire can be compared to water flowing through a pipe. Water will flow from an area of high pressure to an area of lower pressure. This pressure difference represents the difference in electrical potential, which is the force that causes electrons to flow. Voltage, or volts, is a term used to describe the amount of pressure, or force, exerted on an electrical circuit. This is represented by the water level in the pitcher. If we lower the water level, less pressure will be applied to the pipe, just as a lower source voltage applies less pressure to an electrical circuit. Current is the rate at which electrons flow through a conductor and is represented by the water flowing through the pipe. The flow rate of water can be measured in gallons per hour. Electrical current is measured in amperes or amps. If we place a restriction, say a water valve or a turbine in the pipe, the added resistance in the pipe will reduce water flow. Resistance in a circuit works the same way. As we increase resistance, we reduce the current flow. The unit of measurement for electrical resistance is the ohm. The Greek symbol omega is often used on specification charts and technical publications to represent the word ohm or ohms. The charging system on Polaris products use a highly efficient alternating current or AC generator to create voltage. An AC generator consists of a flywheel with magnets and the charging coils or stator assembly. When a magnet is passed by a coil of wire, voltage is induced in the coil through a phenomenon called electromagnetic induction. If there is a complete circuit, current will flow within the wire. When the direction of magnetic field reverses, the flow of current induced in the coil is also reversed. The sine wave shown on this voltmeter represents the alternating current or AC voltage produced by an alternator. At the beginning of the AC cycle, voltage is zero and climbs to a positive maximum. This is the north pole of the magnet passing by the coil. The voltage then drops back to zero and keeps descending to a negative maximum when the south pole of the magnet passes by the coil, after which it returns back to zero. This series of polarity changes is one cycle. AC voltage can supply power to lights and other vehicle loads, but will not charge a battery. A battery supplies a constant polarity voltage known as direct current or DC. If we connected alternating current voltage directly to the battery, the positive half of the wave would charge the battery, while the negative half would discharge the battery. A rectifier changes alternating current into direct current through the use of diodes. A diode is like an electrical check valve, allowing current to flow in one direction and not the other. Polaris personal watercraft have very little electrical demand. For this reason, they can use a simple half-wave rectifier. These rectifiers use a single diode to block the negative half of the sine wave. As you can see, the negative half of the wave is missing. Our EFI snowmobiles and ATVs have a higher electrical demand. On these systems, we use a full-wave rectifier. A full-wave rectifier uses 4 diodes to convert the negative half of the wave to a positive, more efficiently using the AC voltage. As you can see, the negative half of the wave has been converted to a positive pulse. This form of voltage is known as pulsed DC. AC voltage increases with RPM. To prevent damage to system components, we must regulate alternator output to about 14.5 volts. In an AC lighting system, as used on our snowmobiles, the regulator diverts as much voltage pressure as necessary to ground in order to keep from overloading system components. Think of the regulator as an electrical pressure relief valve. The DC regulator supplies the rectifier with as much AC voltage as necessary to maintain a DC supply. This is around 14.5 volts. Even the most difficult charging system problems can be quickly diagnosed if you follow a step-by-step process. First, be sure to get accurate and complete information from the customer. Ask questions that will help the technician narrow down the source of the problem. Questions like, when did the problem first occur? What type of riding does your customer do? Was the vehicle in storage? Was it a sudden problem, or did it occur gradually over time? Once you have a good idea of what you are looking for, you can begin diagnosing the problem. If the customer says the battery is discharged, inspect the condition of the battery and the connections. Check for signs of sulfation, which are white cloudy streaks in one or more cells. Use your meter and test the battery voltage. We recommend the Fluke 73 digital multimeter. It should give you the same results as listed in our technical specifications. Make sure the red lead is in the volts outlet. Turn the selector dial to the DC volt setting, connect the red lead to the battery positive and the black lead to the battery negative. A fully charged battery should read 12.4 volts DC. After recharging the battery, use a hydrometer to test the specific gravity of each cell. Each cell should be at least 1.265. Specific gravity tells us the strength of the acid and is the best indicator of battery condition. In some cases, a battery may show a fully charged state and not function properly. The following load test can be used to test the condition of the battery. Connect the DC voltmeter to the battery as described earlier, and with the kill switch off, engage the starter for 15 seconds. Battery voltage should never fall below 9.5 volts. If the battery was discharged, we need to find out why. A quick test of the charging system is to start and measure the DC voltage at the battery. Connect the DC voltmeter, start the engine, and increase the RPMs. Battery voltage should increase to about 14.5 volts. Everything to this point can be functioning properly, but there may be a residual current draw with the key off. To check this, we need to connect the Fluke amp meter in series with the battery ground cable. With your selector dial on DC amps, connect the red lead to the 10 amp hole on your meter. Then connect the red lead to the battery and the black lead to the ground wire going to the frame. With the key off, you should read less than 0.02 amps. A higher reading indicates excessive current draw. Disconnect non-standard accessories first and then other system components until the excess current goes away. Another way to test an alternator is a break-even test. With the amp meter in series as described above, the meter leads fastened to the battery and ground cable, you should turn on all accessories and observe the current draw created by each one. Start the engine with the recoil only. Do not use the electric starter to start the engine. This will put excessive load on the meter. Never connect or disconnect the amp meter with the engine running. Damage may result to system components such as lights and the rev limiter. Once the engine is running, the Fluke amp meter will show a positive sign if the battery is being charged by the alternator. It will show a negative number if there is a current being drawn from the battery. Increase engine RPM to see if and when the battery starts to charge. This point is called the break-even point. If the customer continuously drives below this RPM, the battery will never charge. The tests we've discussed up to this point will identify problems with the battery and system loads. The following three tests can be used to verify proper output of the alternator. First, the AC open circuit voltage test will indicate the voltage pressure available to the rest of the system. Next, the AC amperage test will simulate full alternator load. The reading observed should be close to the maximum current the alternator can supply. And finally, a resistance check that will test for a short or open circuit in the stator coils and the wires leading to the coils. In order to perform these tests, the alternator output wires must be isolated from the rest of the system. On ATVs with a 150-watt alternator, like this 300 4x4, it would be the yellow and yellow with red wires. Disconnect these wires from the panel and connect them to your Fluke meter leads. For the voltage test, make sure the red lead is in the volts outlet of the meter. Turn the selector dial to the AC volts position. Start and increase the engine RPM. Voltage should be above 20 volts at 3000 RPM. Turn the engine off and move the red lead to the 10 amp outlet. With the selector dial in the AC amps position, start the engine and allow it to idle. Take readings quickly as prolonged current above 10 amps may damage your meter. Compare these readings to the minimum specs listed. If below normal readings have been observed, The coil resistance test should be performed to isolate a problem coil or related wiring. On 200-watt ATV alternators, like the Magnums, test output on the yellow and yellow with red wires. On EFI snowmobiles, use the gray and gray with white wires coming out of the engine. On snowmobile lighting systems, use the yellow and brown wires out of the engine. To test the personal watercraft alternators, disconnect the red with purple and yellow wires in the electrical box and connect a jumper wire between the circuit breaker and a positive battery voltage supply. This provides power for the starter button. For the AC amp test, always make sure the red meter lead is in the 10 amp outlet and the selector dial is switched to the AC amp position. Connect the meter leads to the red with purple and yellow wires coming from the stator and quickly test with the engine running at idle. When faced with a difficult charging system problem, try to isolate the problem from the rest of the system. Is it a battery problem, system load problem, or alternator output problem? Let's recap the tests we've discussed to help find these problems. Get accurate and complete information from the customer and note it on the repair order. Check the condition of the battery. Look for signs of sulfation or corrosion. Make sure all connections are clean and tight. Check the battery voltage. A fully charged battery should read 12.4 volts. Start the engine and increase RPM. Battery voltage should increase to around 14.5 volts. Load test the battery to check reserve capacity. If the battery is discharging in storage, check for current draw with the key off. Check the current draw with the engine running and record the break-even RPM for future reference and comparison. Alternator output can be tested by isolating the stator coil wires from the rest of the system and performing the AC open circuit voltage test, as well as the AC open circuit current test. Use an ohm meter to check the condition of the charging coils and compare these readings to the specifications listed in the Master Repair Manual. Once you have found and repaired the problem, don't forget to go back and verify system operation. We hope this time spent in electrical theory